In this video for Chapter 19, we're actually only going to be talking about Section 19.2. The other parts of this chapter, which deal with how we get the distances to stars, we're actually going to save when we are thinking about larger scales in the portion of the semester where we talk about galaxies. So for now, we're just going to talk about one method out of many that astronomers use to measure distances to stars, which is called stellar parallax. So on Earth, surveyors use geometry and triangulation to determine distances to objects that they can't easily reach. So there are these instruments called theodolites, we don't need to know that name, where the main point of those instruments is to measure angle between the object that you're looking at and the other theodolite that you put down. Because if you can measure the physical baseline between those two surveying instruments and the angles within the triangle, with geometry you have enough pieces of your triangle to get that dashed line physical distance between the tree and where you're standing. Stellar parallax is a way of doing that same kind of idea in space by trying to measure the apparent shift of a star's position against the background stars. It's kind of a tough topic to think about, but parallax is also something that we can fairly easily do with a very quick experiment. So we're going to do this as a group. So what I want you to do is I want you to take your thumb, okay, and I want you to close one eye and cover up something that's kind of on the wall away from you, okay, so that your thumb is perfectly covering it up. And then what I want you to do is to switch which eye is open. Okay, so close the other eye and open the one that you had closed. And go back and forth if you need to. But what I want you to recognize is that your thumb appears to be moving. You're holding your thumb steady, hopefully, but you're covering up a different part of that background picture that you have on your wall, or that background object that you had covered up before. That is also thinking about parallax. So in that thumb and eyeball example, so I can cover up the webcam with my thumb closing one eye, but now it's not covered up anymore. And that example of using your thumb and your two eyes is also a way to think about stellar parallax. Your eye on one side and then the other, that's where the Earth and our telescopes are at one point in Earth's orbit and 6 months later on the other point in Earth's orbit. The thumb is a nearby star that we're trying to make a parallax measurement for, and anything that you can see it moving back and forth across is the background stars. So what we're doing is, if we look at these two blue squares, that red dot is your thumb, and the two different views that you had, your thumb appeared to be in a certain spot, and then it appeared to be in a different spot. We can take those two images and compare them, and the physical change across the sky that we're seeing is related to the parallax angle P. And there is a very simple equation that we can use to think about parallax, which is P equals 1 over D. So the parallax angle is equal to 1 over the actual distance to that star. In order to have such a simple looking equation, we have to use really specific units. The parallax angle has to be in a unit of angle called the arc second. So 1 degree of angle can be broken up into 60 arc minutes, and 1 arc minute of angle can be broken up into 60 arc seconds. So these parallax angles are very, very tiny angles on our sky, where if we imagine looking at one horizon to the other, that's 180 degrees. Each of those degrees has 3,600 arc seconds, so tiny, tiny angles. And then the distance has to be used in parsecs, which is a brand new unit of distance that was designed to make this parallax measurement easy. Because by definition, a parallax angle of 1 arcsecond means that we have defined the distance of a star that is 1 parsec away. 1 parsec is about 3.3 light years. And so when we measure bigger parallax angles, bigger changes, we're looking at stars that are closer by. And when we're looking at smaller parallax angles, smaller changes, we're looking at objects that are farther away. We can use our thumb experiment again. So I want you to try this. So do the thumb experiment twice. Once while you're holding your thumb very close to your face and just see how much change there is from closing one eye to the other. And then having your thumb fully extended and do that same process, and you're going to see a much smaller change. Nearby stars, easy to measure changes. Far away stars, smaller changes, harder to measure. Which means parallax can only be used for nearby stars. The lecture tutorial that we are going to have will walk us through how to think about the parsec and how to think about parallax. I want to make a couple of notes because some students always seem to have a little bit of trouble thinking through what the instructions are having us do. So I'm going to draw on our slide briefly. So I'm going to draw a line. And one of the things it wants us to do is to draw a line from Earth through the nearby star out to the distant stars. And you would draw this on your page. So let me make that a little bit bigger so that we can see it. And then it wants you to do that same thing. It wants you to do that same thing for the Earth 6 months later out to that nearby star and to the distant stars. And so with these two lines that we have here, it is trying to show us that this nearby star will appear to be right where that red star ends. A red line ends. It's going to appear to be against those background stars because it's just in that direction. But 6 months later, it will look like it's in a whole different spot. It will appear to be where that blue line ends, and that overall change is basically describing twice the parallax angle. So that's something that I want us to keep in mind as we try the full lecture tutorial on our own. Now, either using the information that we talked about in the lecture video, or after going through the lecture tutorial and getting a better sense of it, I want you to try this pause and think question. So which of the following stars is closest to us, given those parallax angles? So pause and think. All right, now, this is a really key critical thinking test for us. Even if we don't remember how parallax works, whether this is on the quiz, whether this is on an upcoming assignment or anything, critical thinking should get us far enough to say that if we're at least remembering that parallax tells us about distance, then we can only choose one of the two extreme numbers. We either don't remember how parallax works, so we pick the smallest number, but at least we use critical thinking, or we do remember how parallax works, and we pick the correct answer here, number 4, Sirius, because that had the biggest parallax angle. What we should not have chosen, and I'm not trying to make anyone feel bad if you picked it. I'm not even there in the room, right? But what we should not have picked, and even should not have considered, is options 1 or 2 here, because those number values are just in the middle of the set of 4. We need to use critical thinking in those kinds of situations to at least narrow down our options. That process of narrowing down our options using some parts of what we remember or some parts of using some common sense ideas within astronomy will help us get towards the correct answer. And if we picked Regulus just now, that's okay. We're working on building this understanding of parallax. But we need to spend some more time thinking about this and spend some more time on the lecture tutorial if we need to, if we did pick that incorrect answer, number 3. Now, parallax is the lowest rung of what's called the distance ladder. Now, this image here I really like because it's showing us, in the way that we try to use the word distance ladder, it's showing us that if we want to get to the top of that ladder and be able to make measurements to distant galaxies way, way off at the limits of what we're able to actually see with telescopes, we still have to climb the various rungs between the bottom and the top. Parallax is the most important measurement on the distance ladder because we can only make direct measurements of distance using parallax. All of these other rungs require us to basically calibrate the rung above using information and understanding that we have gathered using the previous or lower rungs of the distance ladder. Now, if we look briefly at what shows up here, so distances of nearby stars determined by stellar parallax reminds us that parallax will not work for stars on the opposite side of the galaxy. They definitely won't work for anything outside of our galaxy. But there are other methods. So there's what's called spectroscopic parallax, and that uses the idea of the Hertzsprung-Russell diagram and where stars are supposed to fall on it. There are star clusters, and we'll talk more about star clusters and how we're able to get a sense of their distance in later chapters. This rung here in the middle, the period luminosity for Cepheid variables, both in our galaxy and then one step up outside of our galaxy, we will definitely talk about those in chapter 25. That's a really, really key and very important topic that's in chapter 20. It's in chapter 19, but we're just not going to talk about it in this video. We're going to save it and kind of come back to it when we need those bigger distances in our brains. And then type 1a supernova, we have to wait until we talk about supernova, and we'll mention that a little more briefly than the Cepheid variables when we get to some of those later chapters, and especially in chapter 29, where type 1a supernova actually helped us realize something key about how the universe is expanding. Okay, so with an eye to the future and bigger and bigger scales as we continue on in our semester, we will close out this section of chapter 19